Hey friends, welcome back to the Journal Feed. My name is Nick Zelton. This is the only place to get spoon-fed the latest and greatest of emergency medicine. We want to keep you guys up on the literature, and we make it easy by spoon-feeding it to you. Now, if you are hearing this right now, then you are not currently a Journal Feed subscriber, and so you will not be receiving the full Journal Feed podcast, only receiving a portion of the past week's articles. Don't worry, all good articles, but if you would like to get full access to both the podcast and the blog, you'll have to become a member. All the details for that are at journalfeed.org. And we don't ever want money to be a barrier to better patient care, so if you have any trouble affording a subscription, get in touch, we'll help you out. This is the audio version of the past week summaries, which this week were brought to you by Megan Hilbert, Seth Walsh-Blackmore, Sam Parnell, and Clay Smith. Okay, what's our first article? Titled A Dirty Dozen 12 P-Value Misconceptions, out of Seminars in Hematology. From time to time, we try to do more than just give you the lowdown on recent literature. We also want to help you understand it. Now, how many people really honestly understand p-values? Statistics, they're hard, and most people don't have a great love for them. After all, many people went into medicine because they like helping people, classically, not because they like math. Or because, they're pretty science-minded and they like biology, and biology is, let's be honest, probably the least math-driven of the major sciences. I definitely know people who hoped to never have to do math again by becoming a doctor. They were, hopefully, at least partly unsuccessful, because I think a basic understanding of statistics is necessary for appraisal of the literature. So let's talk about p-values. Now, if you listen to anything that Ken Milne produces, then you will eventually hear him define the truth. If you think just really quick about the truth superficially, it's easy to be tricked into thinking that there is a right and there is a clear wrong. But, it's never that simple. From a scientific perspective, there is no absolute certainty. Ken Milne likes to put it that the truth is the best point estimate we have of an observed effect size with a confidence interval around that point estimate. But wait, what the heck does that even mean? Well, it means that the truth is just our best guess based on the data that we have to date. And we should be humble in our estimation of the truth by acknowledging that we are probably, right or wrong within a certain range of values, which we call the confidence interval. It's like if I told you that I measured the length of a rope down to the inch. Well, then you would be able to expect me to tell you the length of the rope within about an inch of the true length of the rope, and you would expect to be able to give me a little bit of wiggle room. That concept actually applies to pretty much everything, but most people don't talk about the within an inch part. Whether drug 1 is better than drug 2, there is always some amount of imprecision in everything we know. Statistics is what helps us understand how much confidence we can have in what we measure. One measure of our confidence is the p-value. I think the most confusing thing about a p-value is how people explain the p-value. You'll often hear people say that the p-value is the probability of obtaining results at least as extreme as you've found under the assumption that the null hypothesis is true. I don't know about you, but I think I get most lost around the null hypothesis part. But you can think of statistics kind of like the United States legal system. Essentially, 2 drugs are innocent until proven guilty, which is to say that everything is the same unless you can prove that it's different. That's the null hypothesis, that 2 things are the same. Any other hypothesis is made on a case-by-case basis and pretty much has to be defined. You can remember this just by thinking about the word null. It means 0. It sounds dull. It sounds boring. And what's the most boring thing that there is? Well, having nothing is boring. Having no difference is boring. No difference between 2 things, that's boring. That's the null hypothesis. Okay, back to what the p-value is. Now, knowing that things are null and boring, meaning they're the same, a p-value is the chance that you find at least as big a difference between 2 things, 2 drugs that you measured as you did, or a bigger difference. If your p-value is 0.8, then you know that you have 2 groups which are null. They're the same, they're boring, and there is an 80% chance that the difference that you found between the groups was just due to random chance or because the measuring that you did, well, it's hard to measure things, and it fell within that sort of regular wiggle room. They're not actually two different things. If your p-value is 0.03, then there's only a 3% chance of finding a difference as big as you found or bigger between the two groups, and still being right that they are indeed null, boring, and the same. A 3% chance isn't a very big chance. So odds are the two groups, they're not null, the same, and boring. Really, they're actually interesting. They're different from each other. I've now used the word chance several times, but it's important to keep in mind that chance is randomness, and the p-value isn't a measure of randomness. There are many things that go into measuring a difference between two things. Randomness does indeed influence p-values, but p-values don't quantify randomness. I say this mostly for the really geeky statistics people, because if you make this mistake, I think it has largely an inconsequential influence on your understanding of p-values. So, we need to have decided on which thresholds are okay for p-values. As a completely arbitrary cutoff, medicine as a whole has decided that 5% is our number. And if there's only a 5% chance that things are null, boring, and the same, then that's good enough to convince us that they are in fact different. Thus, a significant p-value is anything less than 0.05. So that's a p-value, assuming I haven't gravely misspoken somewhere in here. What is a p-value not? A significant p-value does not mean that there is a significant clinical difference. I don't think this needs too much explanation, so the numbers say that there's a difference between the two samples, but do you really care about that difference? This ties in to when people call something highly significant, which is weird to say. We've set a threshold of 0.05, so significance is binary. It either is or isn't significant. A lower p-value can raise your confidence in the significance, but it doesn't really make it more significant. Then you decide if you care that it's statistically significant. How much you care, that's probably the real significance. Many people actually question the use of 0.05 as our target p-value, especially since it's arbitrary. Is 0.06 really not good enough for things that are pretty low stakes? Is 0.05 actually even good enough for things that are high stakes? I suppose you can decide, on a case-by-case basis. With the caveat that even though people say it all the time, having a p-value near 0.05 is not a trend towards significance. This is a totally nonsensical thing to say. A trend is something that changes, and the p-value is a static number based on observed data. If you waited longer, there's no reason to think that things would magically become significant. Perhaps your study might have been lacking power, but nothing about the p-value itself can tell you that having more patients in a study would make the effect size significant or not. As an editor to the JournalFeed blog, I should probably be more strict with our authors on this point because they do occasionally use the word trend in this context. For those of our authors who may be listening, take note. In a spoonful, that's the p-value. And then we have the second article titled Antibiotic Exposure and Dental Health, a systematic review out of the Journal of Pediatrics. For all you residents out there, if you're taking a test and they ask you which antibiotic is recommended in pretty much any case and you're not sure at all because it's some kind of weird case, always pick doxycycline. It's probably the right answer, especially if you think it could have anything to do with a tick-borne disease. The exception to this has typically been the use of doxycycline in children because the fear that tetracyclines could discolor their teeth and lead to damage. That would suck because doxycycline is great for treating, like I said, pretty much every tick-borne disease in any age group. The exception is babesiosis. Does it really cause this staining that we're worried about, or is that a worry of the past? These authors did a systematic review of 34 retrospective studies and found no association with doxycycline exposure to children under 8 years old with enamel hypoplasia or dental caries. They didn't even find an association with tooth staining. 18 of the studies dealt with tetracycline or derivatives, and 5 used doxycycline specifically. So what's the deal? Where did this staining thing even come from? Let me tell you that the doses that we used of doxycycline nowadays, they're way, way lower than they used to be before the 1980s where this whole problem began. Let's say I wanted to treat some rickettsial disease or Lyme disease. I would give a child nowadays 2.2 milligrams per kg per day with a maximum of 100 milligrams per dose. They used to give, way back in the day, 20 milligrams per kg per day. That's almost a 10 times higher dose. No wonder they were getting different side effects than we are. It's not that doxycycline can't mess up kids' teeth. It's that it won't at the doses that we give for the durations that we give it, typically less than 3 weeks. The Red Book even agrees. In a spoonful, please give doxycycline to children when they need it. It's a great antibiotic and it won't mess up their teeth, assuming that you give a reasonable prescription. And that ends us off. Let's do our wrap up for the day. From the first article, we talked about p-values and what they mean. From the second article, kids can get doxycycline and it's not going to disfigure their teeth. So go for it. Now, again, if you are hearing this right now, then you are not a part of the members feed and you missed 3 articles from this past week. What were they about? Well, long ultrasound and the diagnosis of ARDS. It can be done, but can it be done well? One of the other articles was looking at, if we took a look at DOACs and stacked them up against warfarin in CKD patients, how would that shake out? And then the last article that you missed was the device RCT, a trial you ought to quote if you want to be an authority on VL versus DL. All the articles summarized from this week can be found at JournalFeed.org, where the newsletter is the best way to make the podcast into a bite-sized nugget of space repetition. Our goal here is for you to read less, learn more, and save lives, one spoonful at a time.